All right, if you're a physics student, you definitely know this feeling. You get the concept, you think you've got it all down, but one tiny plus or minus sign with a mirror problem, and the whole calculation goes wrong. It honestly feels like a secret code sometimes. Well, today we're going to crack it. This is your guide to finally mastering mirror sign conventions. And why is this so important? Because look, these aren't just abstract problems in a textbook. These exact same rules govern everything from massive space telescopes to the passenger side mirror in your car that says objects in mirror are closer than they appear. If you can understand the signs, you can understand how all of these real-world things actually work. I mean, think about it. We can look at an image and describe it with words. We can say it's bigger or upside down or it looks like it's behind the mirror. But to actually do physics, we need to translate those words into a precise mathematical language, and that is the whole point of sign conventions. They're like the grammar rules for the language of optics. So to learn this new language, we have to start with the single most important idea, the one that everything else is built on top of. And that's the difference between a real image and a virtual image. Seriously, if you can get this part down, you are already halfway there. Okay, so what is a real image, really? Well, think about a movie projector. You've got light rays traveling from the projector, and they physically come together. They converge on the screen to form the picture. You can literally put your hand in the path of the light, and the image forms right there on your palm. A real image exists where light rays actually meet in physical space. Now, a virtual image, that's a whole different beast. It's basically an illusion. It's formed where our brains think the light rays are coming from. As you see here, the light rays bounce off the mirror and spread out, but your brain traces those lines back to a single point behind the mirror. There isn't any actual light back there. You can't put a screen there and capture the image. It's just an appearance. And you know what? This right here is something you experience every single day. When you look in the bathroom mirror in the morning, your reflection seems to be on the other side of the glass, right? Light rays from your face bounce off the mirror and hit your eyes. But your brain does the work and constructs that image behind the mirror's surface. That's a perfect, everyday example of a virtual image. Okay, so we've got our two key zones down, right? We have the real space in front of the mirror where the light actually is, and the virtual space behind it where things only appear to be. Now we can use these zones to build our first set of rules for object and image distances. All right, here's the absolute fundamental rule. If you remember just one thing from all this, make it this one. The side of the mirror where the light is actually traveling, where you and the real objects are, that is the positive side. Think of it as the real-world territory. Anything happening on this side is going to get a positive sign. And this diagram really breaks down how that rule works in practice. So, notice the object is in front of the mirror in that real-world zone, so its distance, which we call P, is positive. Now look at the top example. The light rays actually converge in front of the mirror to form a real image, so its distance, Q, is also positive. But now check out the bottom example. The image appears behind the mirror. It's in virtual territory, so its distance, Q, is negative. Simple, right? Positive means real side, negative means virtual side. Great! We've got distances sorted. But what about the mirror itself? Well, the shape of the mirror, whether it curves inward or bulges outward, also has its own sign, and it's absolutely critical for our calculations. So let's put these two side by side. On the left, you've got a concave mirror. It curves inward, like a cave. It takes parallel light rays and brings them together, converges them to a real focal point, right in front of the mirror. And since that focus is on the real, positive side, its focal length F is positive. Now on the right, we have a convex mirror. It bulges outward, and it spreads light out. The rays only appear to come from a focal point that's behind the mirror in virtual land, so its focal length is negative. We're almost there, I promise. We know where an image is, and we know what kind of mirror made it. The very last piece of the puzzle is its orientation. Is it upright, or is it flipped upside down? The sign of the magnification, which we call M, tells us exactly that. So here's the formula for magnification, M. It connects the image and object heights, and also their distances. But here's what I really want you to notice. Look closely at that formula. M equals times negative Q over P. Yep, that minus sign, it is not a typo. Forgetting that sign is probably one of the biggest mistakes students make. It's the essential little link that connects all our distance rules to our orientation rules. It's so important. And what that sign tells you is super straightforward. If you do your calculation and m comes out as a positive number, your image is upright. It's right side up. If m comes out negative, the image is inverted or flipped upside down. So just remember, positive is upright, negative is inverted. That's it. That's the code. Okay, wow, we have covered a ton of ground, right? We've talked about real versus virtual, object and image distances, the different mirror types, and finally, orientation. So now let's pull all of that together into one single powerful summary table. This right here, this is the slide you might want to screenshot or jot down. Let's just do a quick lightning round recap. Object distance P and image distance Q are positive on the real side in front of the mirror and negative on the virtual side behind it. Got it? Focal length F is positive for a converging concave mirror and negative for a diverging convex one. Easy. And finally, magnification M is positive for an upright image and negative for an inverted one. See? This table has everything you need all in one place. All right, let's put this into practice. A quick pop quiz to see if it's all clicking. So you walk into a store and you see yourself in one of those big round security mirrors up in the corner. You notice your reflection is smaller than you are and it's upright. Just from that information, is the mirror's focal length positive or negative? Go on, take a second to think about it. Okay, you're ready? If you said negative, you nailed it. You've totally mastered the signs. Here's the logic. You saw an upright image. Rule check, that means the magnification M must be positive. Now, what kind of mirror always gives you a smaller upright virtual image? A convex mirror. And what does our cheat sheet say about convex mirrors? They have a negative focal length. See how it all connects? Once you know these rules, you start seeing the physics everywhere. What other mirrors will you look at differently now?